Okay, guys, good night. Today we are starting chapter 22. No, sorry, chapter 21 of our A-level chemistry dynamics. It's further equilibrium, as you can see on the screen, in the middle of the screen. So I was so tired yesterday and I didn't record the courses for chapter 21, but I did started chapter 22. But anyway, let's get started. I'll compensate you guys. So as you can hear, I changed my microphone devices, so it's clearer and it's more precise. So let's get started anyway. First, we are gonna to explain 21.1 Kw and pH values. pH values, all of us had heard about that in our daily life, such as pH value of the water, pH value of acid rings, and pH water of milk, blood, or something. So let's give a brief introduction for pH first. This means we will define pH in a scientific way first. pH is negative logarithm to the base 10 of hydrogen ion concentration. So which means the prefix small p means negative logarithm to the base of 10. A more mathematics expression of this will be pH equals to minus log 10 bracket H plus AQ. This looks like this. Remember Remember, this expression means the concentration of aqueous hydrogen ions. So, what are we going to do is to rearrange this formula. So this just ensures that when we know pH value, we can clearly calculate the concentration of H plus ions in the solution. So what are we going to do first is we change the location of negative sign. And then we just cancel logarithm. We do it like this. We use minus pH as the power of 10, as the base is 10. So this just equals to concentration of aqueous hydrogen ions. So this is essential. Just remember this. Yeah, perfect. Okay. Then we are defining Kw. What is Kw? It looks weird. You may recall from our AS chemistry there's a term called Kc. Kc is the constant of equilibrium. So Kw is another form of equilibrium constant, but it's for water. We call it ionic product of water. So what does this mean? What does ionic product mean? This means water is self-deionizing in our daily life at standard pressure and temperature, like this. So two water molecules just form one H3O plus and one OH minus hydroxide ions. and hydroxide ion. So that's basically it, and we can simplify this equation to this. This looks more familiar for all of us. So the Kc for this reaction, I hope none of you don't know this. I hope everyone knows this from AS level. Here, it looks like this. However, you may have a question: how can we know the concentration of water in the solution of water? That's a good question, and I'll explain it in my Clayton Chapter 2 lecturing. We will just introduce a new concept called activity. But for now, you just need to know the concentration of water is very close, so it equals to 1, which means Kc equals to concentration of hydrogen plus times concentration of hydroxide ions. So this is the mathematical expression for Kw. And what's more, at 298 kelvins and 1 atmospheric pressure, Kw equals to 1.0 times 10 to the power of minus 14 mole square decimeter to the power of negative 6. And that's it. So we can rearrange the mathematical expression for Kw. So we get the concentration of hydrogen ions equals to Kw over OH minus, which means when we are desired to calculate the pH of water, we just need to know these two concentrations and Kw. However, if you take a further look at this formula, you'll find an interesting thing. Just a second. I'm sorry. Perfect. You'll find something interesting here. When 1 mole of hydroxide ion is generated, 1 mole of hydrogen plus ion is generated. So, which means the concentration of H plus is equal to concentration of hydroxide ions. So, which means the square of hydroxide ion is Kw, and concentration of hydroxide equals to square root of Kw, since it cannot be negative. So we just cancel another solution for this equation, and then pH is just minus logarithm to the base of 10 square root of Kw. In case of standard pressure and temperature, this value should be this, and we can solve it without using our calculator. It is 7.0, which is reasonable, which just satisfies our experience in our life, because I believe all of you have heard about that the pH of water is 7 before, right? So, I mean, that's just basic chemistry knowledge, and if you don't know this, you don't have to take chemistry. You can just go fuck yourself and begging on street and just try to imagine if someone is going to offer a job for you. So, okay, that's so mean. Oh, that's so mean. Okay, now you maybe wonder, how do we calculate the pH value of acid and base? First, to simplify this question, we are gonna first focus on strong acid and strong bases. The reason why is strong means fully dissociated in water. So we do not have to counting the degree of dissociation when we are calculating the concentration of H plus or hydroxide ions, because we just need to assume that their concentration of H plus or hydroxide ions is equals to their concentration in the solution, isn't it? Okay, for example, we are calculating the pH of HO3, HNO3 aqueous, which has concentration of, let's say, 9.2 times 10 to the power of -4 mole per decimeter cubic. So as we know, this is just monobasic acid, which means there is only one hydroxide ion which can be dissociated in water. A good example would be hydroxide acid and what and never mind. A biobasic acid will be the acid that can release 2 hydrogen ion per molecule. A good example would be sulfuric acid, carbonic acid, or no, just 2 of these are enough. 2 of those are enough. And you see we release 1 hydrogen ion, to be clear here. So which means concentration of H plus equals to concentration of HNO3, which means pH equals to minus log to the logarithm of to the base of 10 of concentration of HNO3, nitric acid. So let's put this value in our calculator. Let's see, how does it work? 9 to the power of negative 4. Oh, system error. Okay. It's 3.04. We don't have a unit for pH because we never have a unit for logarithm and for exponential forms. Okay, that's easy, isn't it? And if you're calculating the pH of a strong base such as sodium hydroxide, we'll say the concentration is also 9.2 times 10 to the power of -4 mole per decimeter cubic. So how are we going to handle this? First, we write the equilibrium equation that it forms in water solvent. We get this nice and easily. So we know the concentration of hydroxide ion equals to concentration of sodium hydroxide. However, since Kw equals to concentration of H plus times concentration of OH minus, so we can say that concentration of H plus equals to Kw over concentration of hydroxide ion. So we just do it like that. I think all of us know that Kw equals to 1.0 times 10 to the power of -14. Okay, perfect. 9.2, I'm sorry. So we get the answer 1.09 times 10 to the power of -11. And so, nice and easily, pH should be 11.0. Yeah, that's pretty simple. So we are turning to our next section. Now we have solved the pH value question, pH value problem with strong acid and strong bases which fully dissociate in water as solvent. Now we are turning to a more complicated question. It's Ka, pKa, and weak acids. Now we are gonna to give you a new definition for Ka. Ka is what I mentioned before. It's the degree of dissociation of an acid or a base in solutions. It's called dissociation constant of acid. It's too hot here in Zagreb. Okay. So, for example, a good example will be ethanoic acid. Yeah, that's the right way to pronounce this. Like this, for example. There is an equilibrium here. So, how to calculate Ka? Ka equals to concentration of this cation, this anion, times concentration of hydrogen plus, and divided by concentration of reactant. So generally we can say for weak acid Ha, it forms H plus and A minus. So Ka for Ha equals to H plus concentration times A minus concentration and divided by concentration of Ha. That's easy. Yeah. So, I need some napkins. Okay. So what are we going to do? What are we going to use Ka for? A good example will be we can calculate pH by Ka. For example, for ethanoic acid at T equals to 298 kelvins, Ka is approximately 1.74 times 10 to the power of minus 5 mole per decimeter cubic. So we can assume that H plus has the same concentration as A minus because of this equilibrium we stated before, which means Ka equals to concentration of H plus square over concentration of the weak acid. So if we want to calculate the pH for Ha, in this case it's ethanoic acid, Ha equals to 0.10 moles decimeter per decimeter cubic, we should do it like this. Ka times concentration of Ha square square root equals to Ha. Concentration of H plus, I'm sorry. Yeah. So pH just equals to minus logarithm of 1.74 times 10 to the power of minus 5 times 0.10 square root to the base of 10. So let's put this value in our calculator and see. It turned out to be 2.88 is the pH value. So that is pretty simple. That's pretty simple. And inversely, we can know as H plus equals to A minus in concentration equals to 10 to the power of minus pH value. So if we know the pH value, we can calculate the Ka, the acid dissociation constant for this under certain conditions. So Ka equals to 10 to the power of minus pH squared, and under concentration of Ha. So we do get this, and we do get this. So that's basically it. That's pretty simple but essential. So we are turning to the next part. 21.3. Acid-base titrations. I have to be quick. And indicators. I think all of you have done paper 3 for Cambridge Chemistry AS level. So in paper 3, there's always a question about titration, and you have to do titration by yourself. So now we have a more scientific definition for titration and its indicators. We don't have to say anything about titration. All of us have learned this in AS level. So let's say indicator, an acid-base indicator. Here, it's a dye or a mixture of dyes. Changes color over a specified pH range. Yeah, for example, you have maybe used methyl blue. It changes color from yellow to blue at the end point of 7.0, I think, but it started change color at the pH of 6.0 and stopped changing at pH value of 7.6. So this satisfies our experience. How does it work? It works like this. There is a chemical equilibrium here. I will use iron as indicator, and look, H ion is color A and H ion minus is color B. So when you are adding more H plus ions, the equilibrium just shift to the left hand side. So we are getting more color A than color B. And if we are adding more OH minus, they cancels H plus and use it up. So the position of equilibrium just shift to the right hand side more. So we get more color B. So we are getting different colors over a range of pH values. That's how it works. Okay, and I have mentioned the word endpoint. Endpoint is where the indicator has a color between two extremes. For example, bromomethyl blue is the end point has the color between blue and yellow. Okay, so we are gonna talk about titration between acid and bases. So previously we just classify acid and bases simply into two categories. One is the weak one, another one is the stronger one, is the strong one. So according to Year 5 mathematics, we have 4 kinds of arrangement. Strong acid and strong base is the first one. And the second is strong acid and weak base. I will just use these shorter versions of words to save time and my electricity. And weak acid and strong base. Then finally we have weak acid and weak base. Just to make it clear, when I'm talking about strong acid and strong base, it's actually strong acid titrated with strong base, which means the strong acid is in the aluminum flask or the volumetric flask under that titration, under that pipette, under that burette, and strong base is filled in our burette. So that's just details. And as I'm lazy, I got some graphs from the textbook for you. Okay, here. Oh, I'm getting too much pictures over here. I believe it's better to draw it by my hand, and it's pretty demanding to draw it manually. So I promise that's not an excuse for myself, but it is easier. Okay, we have to mention a few details for each of those graphs. You can see in strong acid and strong base titration diagram, the starting point is pH approximately is, I'm sorry, I think I got it reversed. So when we are talking about strong acid and strong bases, it's actually we are titrating strong base with strong acid. So in the flask is bases, and in the burette it's strong acid. So the pH initially is approximately 13, which is considered as high, and at the point it's ending, you see pH is approximately 1.0, and the end point is approximately 7, pH equals to 7, which means strong acid and strong bases, strong acid and strong base, they can naturally cancel each other to form a neutral solution when appropriate volume of strong acid is added. So now let's turn to another graph. Here we got strong acid with strong base diagram. You can see it's starting at pH equals to 13 and it's ending at pH equals to 1. The ending point is dependent on the strength of acid, and the starting point is dependent on the strength of that base. As it's a weak base, so we got 13. Oh, no, I'm sorry. We got 11 as our starting point. Okay. See, and we have weak acid with strong base. We are starting again at 13 and we are ending at approximately 4 or 5, I would say. En approximately 4, I would say, which is considered as weak base. Now you can see the ending point is approximately 9. And I forgot to talk about end point here. The end point you see is approximately 4 to 5, which means strong acid cannot be neutralized completely by weak bases, which means when they get equal volume of strong acid and strong bases, there is hydrogen ions in excess. Now we are turning to weak acid and weak bases. So first we're starting at approximately 12, 11 or something, it doesn't matter. And we are ending at approximately 4. So there is actually not a specified endpoint for weak acid and weak bases, because you see that the line has a smaller gradient compared to all of those three previous graphs. So actually we cannot determine the exact value for endpoint. It's somewhere between two values. So okay, now when you see those 4 S-curves, you will see that for strong acid or base you have to draw it like horizontally, and for weak bases or acid we have to draw it like with some gradient. And you see here, weak acid and weak base, we have 2 gradients here. We got 2 gradients here. And if there is some strong things in 2 of those, we have a very rapid change about the midpoint, about the end point. So this is approximately horizontal, and this change is very rapid, so it's pretty accurate. However, here you see it's not vertical. It's a slope, because they are not strong. They don't have a very precise value to obtain for us to obtain. Okay, now that's basically it. And we are talking about buffer solutions then. A buffer means something prevent some overreaction or some vigorous things happen, such as for example, in bungee jumping, you have a buffer just in case those bungee players fall into the ground and die. Yeah, and die. So, as a buffer solution, what's a buffer solution? Analogously, we can say buffer solution is a solution in which the pH doesn't change immediately. Doesn't change significantly. It's better to say significantly. When small amount of acid or base or alkaline are added. One type of buffer solution, it can be weak acid plus its salt. A good example will be ethanoic acid and sodium ethanoate. That will be a good pair of buffer solution. And there is actually another kind of reaction of that kind of mixture to make a buffer solution. For example, a weak base and its conjugate acid. A good example will be ammonia and ammonium chloride. Ammonium chloride is basically the one who provides ammonium ions for the buffer solution. Yeah, so there are two main kinds of buffer solution, and now we are gonna explain how this works. Situation 1. When we add acid, when we add H+, when we are adding H+, I've forgotten, I'm sorry. There is actually an equilibrium like this. Yeah, also like this. These things are familiar for you guys, I believe. So when we are adding acid, we are getting higher concentration of H+. So the position of this equilibrium just shifts to left-hand side. So we are reducing our concentration of H+, which means the pH value got reduced. So when we increase pH a little bit, the pH got reduced immediately. And situation 2. When we are adding alkaline, we have this. So hydroxide combines with hydrogen ions. Oh no, it combines to water, which means it just used up some of those hydrogen ions, which decreases the concentration of H+. So the equilibrium of this, the position of this equilibrium just shift to the right-hand side, which increases the pH. So when we are decreasing the pH by a little bit, the pH got increased immediately. A better explanation would be as we got weak acid and its salt, we always got large reverse supply. I'll write it here. Large reverse supply of ethanoic ions. This ensures concentration of this doesn't change significantly, and it's the same if you substitute ethanoic ions with ethanoic acid, and same here. So because we are getting we have large amount of these two substances, when we are adding small amount of it, the change is in some content it's negligible, which means it doesn't make a big change. Like you are pouring some water into an ocean, it doesn't change the rainfall of Greek, or it doesn't change the tsunami in Japan, right? And now we are calculating the pH for buffer solution. You might be curious about that. Yeah, me the same. How can we calculate pH for buffer solution? It's actually pretty easy. I have to copy the equilibrium here. Copy, paste. Okay, here we got it. Here we got Ka for this. We got Ka for this. It's 1.74 times 10. Oh, I'm sorry. 10 times 10 to sorry oh, the vape is ruining my focus. Oh my god, I have to get into the bike. Okay, Ka equals to 1.74 times 10 to the power of negative 5 mole per decimeter cubic. So we can say that Ka equals to these, the concentration of these times concentration of hydrogen ions, and over the concentration of ethanoic acid, and we're getting this from the concentration of CH3COONA, and we are getting this from concentration of ethanoic acid. So basically we just rearrange this formula and get concentration of hydrogen plus ions, and then we just get pH values by using logarithm to the base of 10. Of course, negative. Don't forget negative. The negative sign just ensures that most of these pH values are positive. They are easier to handle. They look more beautiful, isn't it? And we can get the general form of this equation we just deviated. It's something like this. The form here is basically concentration of hydrogen ions, so don't get panic, don't get scared for this huge thing. And you know, we can split the logarithms by splitting the multiply signs. We do it like this. Oh, 5%, I have to be quicker. We do it like this, and we just see this is exactly pKa. So pH equals to pKa minus logarithm of HA concentration over H minus A minus concentration to the base of 10. This is the final pH equation for a buffer solution. Okay. No, I don't think so. This is correct. I don't think so. This is good. Just a second. No, this is correct, but this can't be our final equation. You know, we can just rearrange this by reversing the fraction there and cancel this negative sign. You know, always think positive like a proton. So chemists prefer to use positive signs instead of negative ones. That's basically it. Now we are going to our final part. Let me see. Oh, I'm writing a lot. We're getting to our final part. It's 20.5, section 21.5, I'm sorry. Is it 20 or 25? Yeah, it is 21. It is 21, okay. So it's solubility. As you know, as predictable, I'll give you another graph here. This graph illustrates that how is solid dissolving in solvent and forms an equilibrium like this. For example, this is an example. This is a picture using silver chloride as a good example. You can see in the solution we got these dissociated ions, and these dissociated ions just came back to reform solid from aqueous states. However, in the solid state, we do have some ions to escape, and turn to aqueous states from solid states, which means when the rate of escaping and trapping ions are equal, we just form an equilibrium. So we can write something like this for solution of a salt. It's AQ, my mistake, my apology. Okay. We are gonna give you a further definition called solubility product, KSP, and solubility product equals to concentration of Ag plus, just in this case, times Cl minus. Okay, we are gonna give you a scientific definition. KSP is product of concentrations for each ions in a saturated solution. Perfect. Of a sparingly soluble salt. At 298 kelvins, which is raised to the power of their relative concentration. Their relative concentration just refers to those numbers in our stoichiometric equations, like, I don't know. We will see. So the most important things are first saturated solution, first product, second saturated solution of sparingly soluble salt, 298 kelvins, and raised to the power of relative concentration. These you have to recite this. This is long sentence, isn't it? A good example will be ferrium sulfide. This is very insoluble salt, extremely insoluble. However, insolubility and solubility are just relative concepts. Just like when we are describing people, he is handsome or he is ugly. Ugly and beautiful, they are just reversed and they're just relative, isn't it? So even though some of those ionic salts may appear to be insoluble, according to our experience, they are indeed soluble, but to a very small extent relatively. So KSP for this should be concentration of Fe3 plus square and concentration of S2 minus to the power of 3. They are raised up to the power of their relative concentrations. That makes sense? That makes sense. Okay, then we are talking about how can we use KSP. First, we can predict if a precipitation will happen. For example, that's just easy. For example, for barium carbonate, KSP is 5.50 times 10 to the power of minus 10 mole square. per decimeter cubic square to the power of -6, which means so we just multiplies two of these concentrations, like the KSP formula gives. So if it's larger, it's larger than KSP, then a precipitation will form. And if it's smaller than KSP, it's in the safe region, so no PPT. That's easy. So we will say what will happen if a barium carbonate solution and there is a cup of barium chloride solution which is unsaturated, and we are adding some sodium carbonate solution inside of it. So common ions effect just take place, which usually or often is more precise, often leads to precipitation. I'll just write PPT to save time and my electricity. First, we have to define common ion effect. It's reduction in solubility of a dissolved salt achieved by adding a solution of a compound which has an ion in common with the dissolved salt. I'll just skip this, that's omissible. This often leads to precipitation, just for emphasizes. So when we are adding barium, we are adding some solution of sodium carbonate into our unsaturated solution of barium chloride. Barium carbonate. There is very high chance of it to lead to precipitation, because when we are adding this solution, we are indeed increasing concentration of carbonate ions, which has a high possibility for this product to be beyond KSP value, and this leads to precipitation. Okay, that's pretty easy, and we have an explanation in the perspective of equilibrium. For example, we got an equation like this. That's just the equilibrium of dissolving of barium carbonate in water. So what will happen if we add more carbonate solution? Just recall the chandelier principle. When we are adding more of these, the position of the equilibrium just shift to right hand side. Yeah, right hand side. So they are more solid. They are more solid produced compared to those aqueous ions, which means the solubility just got decreased. Okay then. So we are coming to section 21.6. I promise this is the last section. Partition coefficient. This is just easy. As you may see, I'll give you a graph here. It's good here. And see, we got ammonium dissolved in organic solvents and water as solvents. So there is actually an equilibrium established by two of these solvents. and the equilibrium is NH3 AQ turns into and turns back to NH3 organic solvent. Similarly, we can say that the K constant, Kc, or in this case we're calling it Kpc, which means partition, partition coefficient equals to NH3 organic solvent, for short OS, and AQ brackets. Don't forget brackets, that's important. So we are getting this. So what can we know from the values of coefficient of partition coefficients? First, if Kpc is smaller than 1, so X is more soluble in B. This refers to a general formula of this equals to XA, which means X dissolved in A and X dissolved in B, like this. So similarly, when partition coefficient is larger than 1, so X is more soluble in A. If it's equals to 0, so they are same, the solubility for X is the same in A and in B. So that's basically it. I would say this section, this chapter, will be pretty easy. And later I'm gonna record a course for chapter 22, but I have to charge my iPad first. Then things are gonna be easy. At chapter 25, we're entering organic chemistry. That's easy work. So goodbye. I'm gonna charge